Welcome to Lecture 3. And in Lecture 3, we're going to talk about the Barabasi-Albert Model. Recall that we learned that the degree distribution of a random graph has a normal curve. So what that means is that most of the vertices have average degree. The degree distribution of a small world graph does not follow the Poisson distribution. That is, its graph is not the normal bell curve. What we want to talk about first before we proceed is what we mean by scale-free property. Now, scale-free would imply that it's independent of a scale. And that's exactly how we can think of it, that if we're looking on multiple scales, we still maintain the small world structure. More formally, we say a network is said to be scale-free if its degree distribution obeys the power law. We saw these curves last time, where the green one represents the normal or the bell curve, which is what a random graph has, and the red one is what we discovered is the degree distribution for a small world network. That is, that most vertices have low degree, not average degree, and then it drops down where there are a few vertices, relatively speaking, of high degree. Now, if we look at these two contrasted with each other in the plot, we can see how different they are. Also notice the equation pointing to the red curve. The p sub k is approximately k to the negative 2.1. What does that mean? Because we haven't talked about that yet. That's what we're about to talk about with the scale-free. Let p sub k denote the probability that a vertex has degree k. Then that probability, when it's approximated by k to the negative gamma power, then we say that this is the power law distribution, and the gamma is its degree exponent. And many naturally occurring networks follow this power law distribution. So in the preceding slide, in this example, the gamma is 2.1. Notice that if we take p sub k is approximately k to the negative gamma, if we take the log of both sides, our exponent negative gamma by the law of logarithms comes down. So the log of p sub k and the log of k are approximately the same except for a negative scalar. Therefore, if you were to plot these, it would just be a straight line with a negative slope. There are some examples where we can see the scale-free plots of two small world networks, and we see the straight line represented. Notice that these are the scales are powers of 10, because this is the log-log plot. Now in this slide, we can observe the two networks, each with their degree distributions plotted above. So if you just randomly connected cities, as we are doing on the left, then the degree distribution would follow the bell curve. On the other hand, if the cities are connected with the small world property, where we have several hubs, but most of the vertices have low degree, then the degree distribution follows the power law distribution. And since it follows the power law distribution, it's scale-free. Now, one of the first reportings of where we find the scale-free was in the 1800s. An economist noticed that a few wealthy people made most of the money, while most people earned much smaller amounts. I think we see that throughout history. The economist was named Vilfredo Pareto. He was an Italian, and his paper became well known, and in the literature, it became known as the 80-20 rule. So we're very familiar, I think, with the 80-20 rule, and this is the first reporting of this power law distribution. There are relatively few that are highly connected, and most of us are not. We talked about what it means to grow a network with one example when we looked at the TR regular graphs. Then we talked about the random graph, which was the Erdős-Rényi model, where you have a graph with n vertices, and the probability of a edge being there is given by a fixed p. And the Watt-Strogatz model, where you start with a regular graph and you rewire the edges. Now, both the random graph of Erdős and Rényi and the Watt-Strogatz graph, both of those were with a fixed number of vertices. The DR regular graph that we introduced in this, but it's not in our text, was our example of how you can grow a network. Now, Barabasi and Albert also noted the shortcoming of the random graph and the Watt-Strogatz graph in that there was no way to grow the graph. So they developed a model of a small world network where you grow the graph. So you can start with an initial amount of vertices. There are no edges. And denoted by n sub naught, so time is 0. You can choose a positive integer m and add a vertex of degree m. That means you'll have to connect your new vertex to m of the existing initial vertices. So m cannot exceed your initial amount of vertices. Now you do this repeatedly. You put in a new vertex and you connect it to m of the vertices. Put in a new vertex, connect it to m of the existing vertices. So after t steps, you have the initial number of vertices plus t new vertices, and you have m times t edges. What emerges from this is a small world network. That is, the older vertices tend to have higher degree, or it's the rich get richer phenomena again. Now, why would you expect this model to produce a small world network? It is, in fact, a small world network. It's scale-free, and it has been shown that the gamma exponent for the Barabasi-Albert model is 3. That is, the probability of a vertex having degree k is k to the negative 3. What would be the possible mechanism for this to happen? But if you think about it, in a social network or in your neighborhood, say in your neighborhood, the people who lived in the neighborhood the longest, they're the ones that are likely to know most of the people in the neighborhood, as opposed to, say, somebody who just moved in. It will take them time to get to know everybody in the neighborhood. Or if there's a paper that's highly cited in the scientific literature, then it's most likely to be read and therefore most likely to be cited again. Or as we are interested in, we're heading towards looking at all these kind of properties in light of biological networks. If you're looking at a metabolic network, then the metabolites that are highly connected, it might be that you could assume that they have the earliest evolutionary origin because they've been there the longest. Now, one thing that we haven't pointed out is how many hubs will you have? So as your network grows, then the hubs or the vertices of high degree keep getting higher and higher. Then at some point, another hub should emerge, because at some point, your hub, the degree of a vertex, cannot be everything like they are with our small world graph in a naturally occurring network. So as the graph grows, you would expect gradually more and more hubs to appear. Now, what drives that? What is the threshold in which new hubs begin to appear? This is unknown, and this is an active area of research in network science. So looking back over the week, we have looked at TR regular graphs, and we looked at them when they were in the form of a complete graph joined to M copies of a set of complete graphs. And the degree distribution for those graphs is discrete because there are only 2 degrees. The vertices in the complete graph of size S were of degree n-1, and the vertices on the periphery in the complete graphs of size P were of degree S plus p-1. We also looked at the Erdős-Rényi graph, or the random graph, which is denoted by G of n comma p. So it's a graph on n vertices where each edge has probability p, and its degree distribution is the normal curve. We looked at the Watt-Strogatz model, which is a rewiring of the regular graph towards randomness, and somewhere between regularity and complete random is a small world emergence. And then in this lecture, we looked at the Barabasi-Albert model, which grows a small world graph by repeatedly adding a vertex of fixed degree. This concludes our introduction into small world graphs.